Hello everyone, welcome to the channel, and today we are going to have our discussion in two parts. In part 1 we are going to discuss the various units and dimensions regarding the electrostatic parameters which we have already learned, and in the second part we are going to discuss about some more advanced concepts regarding electrostatics. So in part 1 of today's discussion we are going to discuss units and dimensions of electrostatic parameters. Now say electrostatic parameters means charges, okay, electric field, electrostatic force, electric permittivity, dielectric constant, Coulombs constant, and so on. So these things are the various electrostatic parameters of our concern. So today we are going to learn the important units and the correlation between the dimensions of those parameters. And in the part 2, as soon as we finish part 1, in part 2 of our discussion, we are going to talk about some advanced concepts of electrostatics. Now both of these topics are very important for competitive exam purpose, because every year 2 or 3 questions appear from these two sections in JEE main and then NEET and other competitive exams also. Especially this part, okay, some advanced concepts are related here, so you can see that it is a very important topic for our discussion today. And today we are going to write a lot, therefore please grab your pen and paper and start writing. So today we are going to start with part 1, that is units and dimensions. So it is not that a lengthy part. This part is going to take some time. Okay. So, part 1, units and dimensions. I have also subdivided this entire topic into 3 categories or 3 subdivisions. Number 1, we are going to define the various charge units. Okay. As we know that internationally we follow 2 major metric systems, which is SI and CGS, and in both of that metric system we have separate units of charges. That is, in SI unit we say the unit of charge is Coulomb, and in CGS that is ESC. So here we first will going to define what is 1 Coulomb and what is 1 ESU. Okay. So by meaning definition I am saying definition of 1 Coulomb and 1 ESU. And having done that, we are going to head forward towards our next topic, which is by far the most important of all these 3. Okay. So that is the relation between, establishing the relation between 1 Coulomb and 1 EC. You see, this topic appears as a question itself in the competitive examinations. So please pay attention while we are doing the relation. Okay. And number 3 is the dimension calculations. So we are going to derive the dimensions of all the electrostatic parameters which we are talking. Okay. Now, let us just start with the definition of various charge units, that is 1 Coulomb and 1 ESU. First, definition of 1 Coulomb. Now there are 2 approaches of defining Coulomb. Okay. Number 1 is the more conventional approach, and number 2 is the derived approach. Okay. So first of all, I am going to write the conventional definition. Conventional definition of 1 Coulomb. Okay. And the definition states as a Coulomb is the quantity of charge a coulomb is the quantity of charge that passes through any cross section of a conductor when 1 ampere current flows through it. For 1 second. Okay, so this is the definition, conventional definition of Coulomb, 1 Coulomb, and it states that a Coulomb is a quantity of charge that passes through any cross section of a conductor when 1 ampere current flows through it for 1 second. You see that I have a conductor here. Let us say that we have taken a cylindrical conductor, and this is some cross section, say the area is A, and some charged particles. These are passing like this, so the velocity of the particle is v, and the governing equation behind this definition is q is equals to I times t. Okay, so we are going to explore this equation in a very detailed manner when we will be studying current electricity, but for the time being consider this to be the governing equation of this definition. So here q is the charge and I is the current, which is for this definition purpose is said to be 1 ampere, and time is 1 second. So therefore the equivalent charge for a current of 1 ampere passing for 1 second is going to be 1 coulomb. Okay, so this is the conventional definition of 1 coulomb. A coulomb is the quantity of charge that passes through any cross section of a conductor when 1 ampere current flows through it for 1 second. So this is the diagram. If you just want to draw it, it's nothing that so. And keep in mind that the cross section has to be consistent. Okay, if the cross sectional area varies for a given time, then the value of the charge might change. Okay, so it is only constant here. Otherwise, the definition is quite foolproof. And this is the conventional definition of coulomb. Okay, so please write it down. A coulomb is the quantity of charge that passes through any cross section of a conductor when 1 ampere current flows through it for 1 second. Okay, so now the second definition. In the second definition, we are not just going to write the definition directly, but instead we are going to derive the conditions required for the derivation. Now this kind of definition where we derive some conditions is called the definition by criterion. That is, we are going to set some conditions for which the definition is going to be applicable for. Okay, so for doing so, I am going to write the formal equation of Coulomb's law. You know that Coulomb's law states that any two point charge particles will exert an amount of electrostatic force with each other upon each other when they are separated for a distance of say r. So the formulae is like that: the electrostatic force F is going to be 1 over 4 pi epsilon naught into Q1 Q2 divided by r square. So this is the Coulomb's formal equation. Here Q1 and Q2 are the 2 point charges and their separation between them is r, and the electrostatic force acting between these 2 point charge particles is given as F is equals to 1 over 4 pi epsilon naught into Q1 Q2 by r square. Now this entire thing, okay, this entire section, it is known to be a constant. This constant is known as Coulomb's constant. So this is the Coulomb's constant. Coulomb's constant. And in this constant there is also another property. This is called the electric permittivity. Electric permittivity. Now we are using the free space to be the medium for our experiment or our definition. So as we are using the free space, we are using epsilon naught. Epsilon naught is the electric permittivity of free space. And in the previous video I have already discussed that there is a constant value of epsilon naught, that is 8.85 into 10 to the power minus 12 Coulomb square per Newton meter square. This is the unit of epsilon naught, and the value is epsilon naught is equals to 8.85 into 10 to the power minus 12 Coulomb square per Newton meter square. And accordingly, if we just derive the value of 1 over 4 pi epsilon naught, it is going to be 1 by 4 into 3.14 into 8.85 into 10 to the power minus 12, and the value is, which we obtained as 9 into 10 to the power 9, and the unit. Now you can see that the electric permittivity is in the denominator of the fraction or the ratio, and as the unit of the epsilon is Coulomb square per Newton meter square, the entire unit of this Coulombs constant is going to be the reciprocal of this. Okay, so the unit is just going to be inverted, and the unit is Newton meter square per Coulomb square. So this is the unit of 1 over 4 by epsilon naught, or the Coulombs constant. And like epsilon, Coulombs constant is also constant for free space, because if the medium changes depending upon the value of epsilon of that medium, the value of Coulombs constant is going to be changing, and it keeps on changing. And as we change the medium from free space to something else, the value of the Coulombs constant is actually going to be decreasing, because the epsilon is going to increase for any other medium other than the free space. So we are going to use this value of Coulombs constant in this equation. So just put the value there. So after putting the value, the equation stands like this: F is equals to 9 into 10 to the power 9 into Q1 Q2 divided by R square. Now our objective is to find the definition of 1 Coulomb. That means somehow we have to manage this Q1 and Q2 to become 1 from this equation. It is obvious. So that for that condition we are considering like charges. Now like charges means the magnitude and the nature of the charges are going to be the same. Okay. So these are equal and similar charges. And if so, then of course equal and similar charges, or the like charges, will repel each other. Okay. So let us consider the charge Q1 is equals to Q2 is equals to, say, Q. Then the equation is going to become 9 into 10 to the power 9 Q square over R square, cross multiply R over here, and we get Q square is equals to FR square divided by 9 into 10 to the power 9. Now our objective of this definition is to bring the definition of 1 Coulomb. Therefore this Q square is, the value of this Q square has to be equals to 1. So therefore put equals to 1, and for that condition this FR square divided by 9 times 10 to the power 9 is also going to be 1. So FR square divided by 9 into 10 to the power 9 is equals to 1, or FR square is equals to 9 times 10 to the power 9. Now if we take the separation between these two charges to be 1 meter, that is these two charges are separated for the distance of 1 meter in vacuum, then R square is going to be 1. Okay, R square is going to be 1 for separation of 1 meter. Therefore if this R square becomes 1, then the value of F is 9 times 10 to the power 9. And as we know that F is the electrostatic force acting between the point charge particles, and in SI metric system the unit of force is Newton. Therefore it is actually 9 times 10 to the power 9 Newton. The huge amount of force that will going to act between 2 point charge particles of 1 Coulomb. So this is a conditional definition or definition by criterion where we set the condition for the charges to be 1 Coulomb. And the definition is going to be like this, that if the charges are of 1 Coulomb and then if they are separated for a distance of 1 meter in vacuum, then they are going to experience the amount of force which is equals to 9 times 10 to the power 9. So therefore, if two charges, if they are similar and if they are placed in vacuum and the distance between them is 1 meter, and if they are experiencing a force of 9 times 10 to the power 9, then of course the value of those charges is going to be 1 Coulomb. So this is actually the inference method which we have used here to deduce the definition of 1 Coulomb. Okay. So let me write it down, the definition. Okay, you got the whole thing, I hope, that what we have done here is to find the definition of 1 Coulomb. Instead of using the conventional method, we put the value 1 and then we found out what is the exact condition for the charges to be 1 Coulomb. And the definition comes out like this: if two charges are placed at a separation of 1 meter, okay, if two like charges are placed at a separation of 1 meter in vacuum, and if they are experiencing a force of 9 times 10 to the power 9, then of course the value of each of the charges is going to be 1 Coulomb. Okay? Good. So let us just write down the definition. So it is the amount of charge, for which two like charges kept in vacuum and separated at a distance of 1 meter. Okay, it is the amount of charge, it is the amount of charge for which two like charges kept in vacuum and separated at a distance of 1 meter will experience a net force of 9 times 10 to the power 9 Newton. Okay, so this is the derived definition of 1 Coulomb, and it states that it is the amount of charge for which two like charges kept in vacuum and separated at a distance of 1 meter will experience a net force of 9 times 10 to the power 9 Newton. So this is the derived definition of 1 Coulomb. Okay. So now we are going to see the definition of 1 ESU. Okay. So this is the unit of charge in CGS metric system, and in case of CGS metric system, the form of Coulomb's law can be written as Kf is equals to 1 by K into Q1 Q2 divided by R square. Okay. So here K is the dielectric constant of the medium. Dielectric constant of the medium. And for defining the charge units in ESU, we also are going to use the condition which we have discussed earlier, that is, we are consider like charges. And by telling like charges, I mean that Q1 is equals to Q2 is equals to Q. Okay. So this is the definition. Now, for free space, K is equals to 1, that is the dielectric constant for free space or vacuum is going to be equals to 1. So therefore the force become F is equals to Q square by R square. Now if the charges are separated at a distance of 1 centimeter, then R is equals to 1. Okay. Now if the charges are separated at a distance of 1 centimeter, okay, then becoming R is equals to 1, we can say that F is equals to Q square. And as F becomes equals to Q square, so if F is equals to 1, then only Q square is going to be equal to 1. That means that for Q becoming 1, we need to put the value of F to be 1, and F 1 means F is equals to 1 dyne. Okay, so the definition of ESU in case of CGS metric system requires the force between those two charged particles to be 1 dyne. Therefore the definition is going to be like this, that we have two charges, two like charges which are separated at a distance of 1 centimeter, and then we place it in a vacuum, and the force they are going to experience is going to be 1 dyne. Okay, so this is the definition of 1 ESU, and I am going to write the definition. Just copy it down. Okay. So the definition of ESU goes like this, that it is the amount of charge for which two like charged particles or two like charges kept in vacuum and separated at a distance of 1 centimeter will experience a force of 1 dyne. Now here also the force, the nature of the force is going to be repulsive, because we are using like charges. So as we are using like charges, the amount of force is going to be 1 dyne, and the nature of the force is going to be repulsive. So this is the definition of 1 ESU, and it states that it is the amount of charge for which two like charges kept in vacuum and separated at a distance of 1 centimeter will experience a force of 1 dyne. Okay, so this is the definition of 1 ESU. Please write it down. Okay, so this is the definition of 1 ESU. It states that it is the amount of charge for which two like charges kept in vacuum and separated at a distance of 1 centimeter will experience a force of 1 dyne, and the nature of the force is repulsive. So hopefully you all have written that. Now we are going to derive the relation between 1 Coulomb and 1 ESU. Okay. So our definition part is over. Now it is time for the relation between one Coulomb and 1 ESU. By knowing the definitions, the derivation of this relation is going to be quite easy. The first thing we need to know before doing this derivation is that the relation between Newton and dyne. Relation between Newton and dyne. and the relation is 1 Newton is equivalent of 10 to the power 5 dyne. This is in this is in SI and this is in CGS metric system, and the relation between Newton and dyne is 1 Newton is equivalent of 10 to the power 5 dyne, and therefore 9 times 10 to the power 9 Newton force will be equivalent of 9 times 10 to the power 14 dyne. Just multiply it to this part with 10 to the power 5 and you will get that the 9 times 10 to the power 9 amount of force is equivalent to the 9 into 10 to the power 14 dynes of force. Okay. Now, and also we know that 1 meter is equals to 100 centimeter. Okay. So, as we know that the force experienced by 2-point charges, the force experienced by 1 Coulomb charges is 9 times 10 to the power 9 Newton. Okay, so we are going to use this information here. So, we have seen that 9 times 10 to the power 9 Newton is actually equal to 9 into 10 to the power 14 dynes. Now, as we are trying to establish a relation between 1 Coulomb and 1 ESU, therefore we assume that 1 Coulomb is equals to n stat Coulomb or n ESC. N stat Coulomb or ESC. Okay, so here we have 1 Coulomb is equals to n stat Coulomb. Therefore 9 times 10 to the power 9 Newton, 9 times 10 to the power 14, this is the value of force in dyne, is equals to 1 over k, which is equals to 1 into n square by 1 meter square. Okay, so we are actually using the CGS method, that is F is equals to 1 by K times Q square by R square. It is the same structure. Only the amount of force is 9 times 10 to the power 14 because the force experienced by 1 Coulomb charge is 9 times 10 to the power 9 Coulomb, and it is in dyne, it is 9 times 10 to the power 14, and as we are using stat Coulombs and 1 Coulomb is equals to n stat Coulomb according to our assumption, therefore we have put n square because we are using like charges. Okay, considering like charges. So as we are considering like charges, therefore this is going to be n square, and the separation between two charges of 1 Coulomb is 1 meter, we know that, for this amount of force, that is 9 times 10 to the power 9, and this force 9 times 10 to the power 14 is equals to 1 by 1, that is k equals to 1 for free space we know, and n square divided by 100 square, because we have seen that 1 meter is equals to 100 centimeters, and multiply this with 9 times 10 to the power 4, we get n square is equals to 9 times 10 to the power, it's 4, and plus 14 is becoming 18. Okay, so 9 times 10 to the power 18, therefore n is equals to 3 into 10 to the power 9. So this is the value of n, and we have assumed that 1 Coulomb is equals to n stat Coulomb, and as n is 3 times 10 to the power 9, then we can write that 1 Coulomb is equals to 3 times 10 to the power 9 ESU or stat Coulomb. Okay, so what we have done here, the force experienced by 1 Coulomb charge is 9 times 10 to the power 9 Newton, and we have assumed that 1 Coulomb is equivalent of n stat Coulomb, that is ESU, and we are using the CGS metric system format of Coulomb's law, that is F is equals to F being the electrostatic force acting between those 2 point charge particles, and F is equivalent to 1 by K times Q square by R square, and here the 1 coulomb charges are being separated at a distance of 1 meter, and according to the conversion, the scale conversion, 1 meter is equivalent of 100 centimeters, and we have put that value of 100 centimeters and it's being squared. And as we are using considering like charges, therefore 2 1 coulomb charges is going to be n square. Okay, for 1 coulomb to stat coulomb conversion, there is going to be n square in the numerator, and the amount of force is going to be 9 times 10 to the power 14 dyne, because in recently we have seen that 1 Newton is equivalent of 10 to the power 5 dyne. So 9 times 10 to the power 14 is equals to n square by 100 square. Therefore n square is becoming 9 times 10 to the power 18, and the value of n is 3 into 10 to the power 9. And as the value of n is like that, therefore we can say that 1 coulomb is equivalent of 3 times 10 to the power 9 ESU. Okay, so this is the relation between 1 coulomb and 1 ESU. So please write it down, and I must tell you that this relation is very important. Okay, itself it comes as a question in the competitive examinations, so it is very important. Please copy it correctly. Okay, so now that we have seen the relation between 1 coulomb and 1 ESU, let us head forward to the third category of our discussion, that is the dimensions. Now, dimensions. First, start with charge. The dimension of charge is given as I into T. Okay, so here I is the current, that is dimension of current, and T is the dimension of time. So as you can see that charge is a derived dimension. It is not a fundamental or primary dimension, it is a derived dimension. Now the question is that you can ask that although charge is a fundamental quantity, it is an intrinsic property, okay, you cannot separate charge from its mass, okay, so it is that much of primary or fundamental thing, then why we are not actually having the dimension of the primary dimension of charge itself? Because why we are deriving the dimension of charge? Now the fact is that although charge is a fundamental quantity, we cannot measure it directly, and the dimensions which we actually talk about, the primary dimensions which we consider in our daily life, such as mass, we can measure it, such as length, we can measure it, time, we can measure it, current, we can measure it, but we cannot actually measure the charge itself. Okay, so the measurement of charge is very difficult, and actually how much charge is flowing from one place to another is being measured using the current through a conductor. That is, already I have discussed this equation earlier. So this equation itself is a dimensional equation. Okay, so actually we can measure the current through galvanometers and through voltmeters and so on, the ammeters. So we can measure the current and we can measure the time, and by using those two parameters we actually derive the dimension of charge. But we cannot directly measure charge itself. That is why it is not a primary dimension. Dimensionally it is not a primary quantity, but physically it is a fundamental constituent of matter itself, and it is a fundamental property of matter, although it is not a primary dimension. Okay, so this is the dimension of charge. Now let us say the dimension of force. We know that electrostatic force is a kind of force, and the dimension of force is given as mLT times minus 2. It is the dimension of force, and electrostatic force is also the same, and therefore the dimension is also same. The third one is, which is we are going to derive, is electric permittivity. Electric permittivity, epsilon. The dimension of epsilon is very interesting because the unit says Coulomb square per Newton meter square. Okay, so Coulomb square means charge square, and charge has a dimension of IT, therefore it will be I square T square divided by Newton is the unit of force, and the dimension of force is mLt to the power minus 2. So it is going to be mLt times minus 2 into meter square, and the dimension of meter is L, so it is going to be L square. So see, there is one m in the denominator, L cube in the denominator, t to the power minus 2 in the denominator, and t square in the numerator, and I square in the numerator, and all the calculations end up that the dimension is actually m to the power minus 1, L to the power minus 3, I square t times 4, t to the power 4. Okay. So this is the ultimate dimension of electric permittivity, epsilon, which is m to the power minus 1, L to the power minus 3, I square t to the power 4. Okay. Now, please write it down, and then we are going to derive the dimension of Coulombs constant. Coulombs constant, we have already seen at least 1, 2, 3 parameters. Now this is the fourth one, which is Coulombs constant. Coulombs constant. And the dimension of Coulombs constant is going to be, we have seen that it is 1 over 4 pi epsilon naught, and the unit is Newton meter square per Coulomb square. The unit of the unit of force is Newton, and the dimension is mLt to the power minus 2, and the dimension of meter square is L square, and it is divided by charge, that is I square t square. Okay, so the dimension becomes m L cube I to the power minus 2 and t to the power minus 4. Okay, so this is the dimension of Coulombs constant, that is 1 over 4 pi epsilon naught. Okay, so this is the dimension. Please write it down. Okay, now we are going to derive the dimension of surface charge density. Okay, surface charge density. As we have learned earlier that surface charge density sigma is equal to q by A. Okay, it is charge per unit area. So the surface charge density sigma is given by the charge per unit area, and the dimension of charge is, as we know, I times t, and the dimension of area is meter square, that is L square. So the dimension is going to be m to the power 0, L to the power minus 2 I times t. So it is the dimension of surface charge density sigma. Okay, it is given by charge per unit area, that is q by A, and the dimension of q is I times t, and it is divided by the dimension of area, which is L square, and the resultant dimension is m to the power 0, L to the power minus 2 I times t. Okay, so this is the dimension of surface charge density. And the next dimension we are going to calculate is electric field. Electric field. Now the dimension of electric field, the unit of electric field, can be given in several other ways, but the most promising or the most shortest unit is that it can be given as, the unit is Newton per Coulomb. Okay, it is the shortest unit of electric field, and according to that the dimension can be, the dimension of force is m L t times minus 2, and Coulomb, we see the unit of charge, and it has a dimension of I times t. So the resultant dimension is going to be m L and I to the power minus 1 times t to the power minus 3. So this is the dimension of electric field E. It is a vector quantity, and the dimension of electric field is m l I to the power minus 1 times t to the power minus 3. Okay, so it is the dimension of electric field. Now here we are not actually going to study the dimension of electric potential. Okay, we are going to do that whenever we are going to study electric potential as a separate chapter. We are going to discuss them. Okay, so these are the primary dimensions, and we have successfully completed our parts. The discussion of part 1 is complete. Now we are going to head forward towards the second part of our discussion.